All right, let's talk about the variance of beta hat. So in last class, we derived the expectation of beta hat, and we used that to help us decide whether or not beta hat was an unbiased estimator for beta, which it was. And now we'd like to show that the variance of beta hat is the minimum, so it's the best, that beta hat is really the best estimator. And so to do that, we need to obviously know what the variance is before we can determine if it's the smallest among the linear unbiased estimators. So the first thing we're going to use is something called the Law of Total Variance. And so in the last class, we used something called the Law of Iterated Expectation or the Law of Total Expectation. And there's a similar proof for variances. There's a similar law for variances that basically says that we can split up a variance into two components. So the variance of x is always going to be equal to this summation here, the expectation of the variance of x given y plus the variance of the expectation of x given y. So what this is saying is basically a variance can be split into the variance, a conditional variance, the expectation of a conditional variance, plus the variance of a conditional expectation. So we're going to use this to be able to calculate the variance of beta hat. So the variance of beta hat is going to be equal to the expectation of the variance of beta hat given x plus the variance of the expectation of beta hat given x. So we definitely know one of the parts of this equation. What is the expectation of beta hat given x? It's beta. We just spent all of last class solving for it. This is what lets us know that beta hat is unbiased. It's an unbiased estimator for beta. So the expectation of beta hat given x is beta. And is this constant or random? So think back to that last lecture, or if you don't remember, you can pause this and go back and watch it. But try to decide, is beta constant or is beta random? Beta is constant. So beta hat is random, but beta is constant. So what does that mean? Well, what is the variance of a constant? So variance describes variability or the spread of something. So if it's just constant, then there's not going to be any variability. So the variance is just going to be 0. So we can cross out that second part of the equation and just replace it with 0. And so now we know that the variance of beta hat is actually equal to the expectation of the variance of beta hat given x. So this simplifies our problem and means we can just sort of solve for this inner variance here, the variance of beta hat given x. So that's what we're going to do. So let's focus on this inside part, the variance of beta hat given x. So I filled it in here, the variance for what beta hat is. Beta hat is x transpose x inverse, x transpose y. And so I've just rewritten this expression with that. So the variance of x transpose x inverse x transpose y given x. So what's constant and what's random in this? So these x's here are going to be constant because that is what we know because it's given x. And this y, if you recall from our previous lecture, that's going to be random. And so because this x transpose x inverse x transpose is constant, we can apply our variance rules that we covered in the previous lecture that basically show that if you have some constant multiplied by some random variable and you're taking the variance of it, you can extract that constant, and if it's a scalar, it will end up being just the constant squared. But if it's a matrix, like in this case, you'll end up pulling the matrix one time on the left side of your equation, and then you'll transpose it and pull it out on the right. So this is sort of like the equivalent of taking the square if this was a scalar, but since we're in matrix land, we pull out kind of, like you could imagine you could replace this whole thing with just the letter A. So if we replace this whole thing with the letter A, then this would be A times the variance of y given x, and so that's the variance of our random part, times A transpose. And so that's what we've done here. We've got our x transpose x inverse x transpose. That's pulled out here on the left. And then if we take the transpose of this thing, we end up getting x times x transpose x inverse. Now, one other piece of important information here is that the variance of y given x, this is defined as sigma squared. That's just the symbol we often use for the variance of y given x. So I'm just going to plug that in there. And so this is what we get. We end up with the x transpose x inverse x transpose times sigma squared times x transpose x inverse. And so it turns out that this sigma squared is a scalar, so we can pull it out to the front. And with that allows us to cancel some things out here. So we can pull this sigma squared out, and then we can cancel out this x transpose x inverse times x transpose x. Because this here is basically just this is the equivalent of basically dividing by the same thing. So we end up with just sigma squared times x transpose x inverse. And there you have it. So that is our variance of beta hat given x. And so we know that the variance of beta hat is equal to the expectation of the variance of beta hat given x, which is equal to the expectation of sigma squared times x transpose x inverse. Again, what is a constant here? Well, it turns out everything here is constant, and so we can redefine this as the variance of beta hat is sigma squared times x transpose x inverse.